Hi, welcome back. I am Ahmed Mahmoud, Head of Data Engineering at DataMindAI, and welcome to the Large Language Model series. If you work in data, AI, analytics, or decision science, the last 2 years have been there's a lot of changes everywhere in your field. Large language model or LLM are not a trend anymore. They are a fundamental shift in what software can do and what your role will look like in 3 years. So this series is built for practitioners, not theory for its own sake, but the understanding you need to make real decisions, which model to use, when to build versus buy, how to estimate costs, and how to deploy these systems safely and effectively. We go from the absolute foundation, how machine learn, how language becomes numbers, and all the way through a technical deep dive on a training cost, the top 10 models in production today, and the architecture reshaping the entire field. Now, because this is a hands-on series, we also have a practical session where we apply these concepts directly to real workflow, real prompts, and real use cases. So it's not bluff, no bluff here, no jargon for its own sake, just the stuff that matters. And I'm glad you are here. So let us get into the LLM side, the technical side of LLM. Welcome back to the technical deep dive. This session is for people who make real decisions, which model to deploy, whether to train or fine tune or call an API call, how to estimate costs, and how to evaluate vendor capabilities claim critically. So we are going to ground everything in real numbers and be explicit about what it is published and what is estimated and what companies have deliberately not disclosed. Three questions frame this session. One is, how is an LLM built from data collection through pre-training, fine-tuning, and alignments? And then number two is like, what does training actually cost in hardware, compute, electricity, and time? We will work through the math for real models. Now, number three, who are the key players here? What are their models and how do you compare them for a specific use case? Now, why cost structure matters to architecture? You might ask, why should a solution architect care what a training run costs? Yeah, they will never train a frontier model. The answer is because cost structure shapes vendor product decisions, which shapes your architectural constraints. I'm going to repeat here because cost structure is going to shape the vendor product decisions. Yeah. And this one also will shape your architectural constraints. So when a company trains a model for 200 million, yeah, dollars, they need to amortize that investment across millions of users. That drives the API pricing decision, their rate limiting, their context window choices. Understanding the cost structure helps you predict how vendors will behave, evaluate whether 14 cents per million token price is sustainable or loss leading, and choose vendors who will still exist in 3 years. Now, understanding the training pipeline also helps you understand model failure modes. Yeah, a model with a knowledge cut of April 2024 will confidently hallucinate about anything that happens after that date. So a model trained predominantly on English will be weaker on low resource languages. Training determines failure. Knowing the training knows you the failure as well. Now, let us start with the big picture, the full-scale metrics that defines the landscape of models in production today. The scale of modern LLMs. So this table is a reference framework, not a set of precise figures. I must emphasize here, it's not the figure you see there is not precise. The numbers represent informed consensus from the published papers, analyst estimates, and occasional company disclosures. Treat them as order of magnitude estimate with roughly plus or minus 50% uncertainty. No frontier lab, because no frontier lab publishes details training cost breakdown. So that will be clear here. Now, the metrics we are going to use is like parameters, how many parameters are using, the training token, the training cost, also GPU days, GPU required, and real examples, for example. Yeah, so let us look at these areas. So the key insight is 4 orders of magnitude here. Yeah. So what we say is like small, medium, large, and frontier, for example. Yes, so 4 orders of magnitude separates the smallest and largest model in production. Yeah, today, for example, you have 7 billion model costing. Yeah, as you can see, $500,000 to train, $500,000 to train, running on a single GPU. Sits in the same category as a frontier system, which is the last one, costing $500,000 and requiring a supercomputer cluster. We should use an LLM is not a decision with a single cost profile. Now, what the table omits here is the hidden cost multiplier. The table shows the final training run cost. Yeah, this is the most misleading number in LLM economics. For every successful training run, there are typically 10 to 20 failed or suboptimal runs during the research and development phase. So testing different hyperparameter settings, different data mixture, different architecture choice. Now, Google Gemini Ultra reportedly required these complete training runs before converting to the final model. So each run cost over 100 million. So the successful run was 1/3 of the total training cost. So when you add data collection, cleaning, and deduplication, which is 1 to 3 months of engineering, human labeling for RLF, tens of thousands of hours at 15 to 20 dollars per hour, safety and capability evaluation, 6 to 12 months for a frontier model, infrastructure setup, and amortized hardware. So the true total development cost for a frontier model is 3 to 10 times the headline training figure. So the total cost to bring GPT-4 from concept to deployment was likely over 1 billion. So the small model revolution is strategically more important. While headlines are dominated by frontier model cost, the strategically significant trend for most organizations is the small end of this table, a 7 billion parameter model running locally on a single A100 GPU Llama 3 8B, Queen 2.57B can handle a wide range of enterprise tasks with sub-second latency, zero data leaving premises risk, and a per query cost measured in fraction of a cent. Now, for healthcare, legal, and financial application where data sovereignty is non-negotiable, this is not a compromise, it is a correct architectural choice. So let us go deeper on the most important metrics in this table. Now, what are parameters here? So precise technical definition for a parameter is a single scalar floating point value within weight matrix of a neural network adjusted during training via gradient descent to minimize the loss function on the training data. So in practice, an LLM consists of multiple layers of matrix multiplication, layer normalization, and non-layer activation. So the parameter are the elements of those weight matrix, yeah, during the forward pass. Input embeddings are multiplied by these matrices at each layer. So during the backward passes, the gradient of the loss with respect to each parameter is computed. So and each parameter is adjusted indefinitely in the direction that reduces the loss. So after training converges, parameters are frozen. The frozen weights are the model. So now the storage, again, let me come back to this parameter here. I mean, even though it looks like a bit complicated, but let me give you like one analogy. For example, in a normal mathematical graph, for example, it is just you say y is equal mx plus c, y being the y-axis, x being the x-axis, and m is the gradient, and the c is the constant for the gradient. So here you will have two parameters, as it were, which you can change to change the look of the graph. So you can go to positive, negative. You can add like numbers. So that's like that is how we do it. So that is how you do, for example, in a simple graph. So we are talking now here with this neural network where you have similar parameters, yeah. So in here, billions of them, where you change like you give like a starting number, and then you apply all these parameters onto the equation, and they give you a result, and you compare it with the, for example, with what you want, and then if it's far away, you go back and change the number, yeah, you started with, yeah, the number of parameters, yeah. So these are this changing we are talking about now. So we have billions of parameters here. So so it, because the LLM consists of multiple layers of matrix multiplication, so layer normalization and non-linear activation. So the parameters are the elements of those weight matrix. So during the forward pass, input embeddings are multiplied by these matrix at each layer. So, and then you see the result. So during the backward pass, the gradient of the loss with respect to each parameter is computed, and each parameter is adjusted. Yeah. Uh, in the direction that reduces the loss. So after training converges, the parameters are frozen, and the frozen weights are the model. Yeah. So the storage format and their practical implication. Now, the storage format directly determines memory requirements. So FP32, which is 4-byte parameter per parameter. So each parameter will have like 4 bytes. Yeah. So you will have 175 billion parameters, for example, would require 700 GB. Yeah. Original training precision. Now, the F16, which has 2 bytes per parameter, with the parameter now is like 175 billion parameters now. So they will require 350 GB, which is standard for inference. So now the INT8, which is 1 byte per parameter, would require 175 GB. Requires calibration, competitive quality. So the int4, which with 0.5 bytes per parameter, would require like 87 GB, acceptable for many tasks, not all. Now, ENT4 quantization is why Llama 3 70B can run on two consumer A100 GPU instead of requiring 8 enterprise-grade ones. So the quality trade-off, negligible for classification and extraction, noticeable for complex multi-step reasoning. Now, what parameters encode and critically what they do not? Common misconception is parameters store facts like a database. They don't. Parameters encode a statistical pattern. So the distributional properties of language as observed in the training corpus, for example. Yeah. So the model does not have a database row saying Paris is equal capital of France. It has a configuration of parameters such that when the sequence, the capital of France is processed, the probability distribution over the next token strongly picks at Paris. Yeah. So the knowledge is implicit, now distributed across billions of weights, not stored explicitly anywhere. This is why hallucination exists. If the training data contained like consistent, accurate information about a topic, the relevant parameters are well calibrated. If the training data contains conflicting or sparse information, the parameters may be poorly calibrated and the model will produce a confident sounding but incorrect answer because the confident predictions are statistically what well-calibrated parameters produce. Now, hallucination is not a software bug. It is an inherent property of a system that interpolates between training examples using a statistical pattern. Grounding through RAG or tool use is the engineering solution when factual reliability is required. Now, parameters need data and compute to be so the parameters need the data and the compute to be trained. Yeah, let us look at the fundamental relationship between these three resources, a relationship that triggers one of the largest investment waves in technology history. Now, in 2020, Kaplan at OpenAI published a scaling law for neural language models. Now, its central findings, model performance improves as a smooth power law with parameters, training data, and compute. Now, the improvement is predictable across many orders of magnitude. This finding had enormous consequences. It meant that building better models was primarily an engineering and funding problem, not a fundamental research problem. If you could predict in advance how much better a large model would be, and the prediction was reliable, you could justify like for example, spending 100 million instead of 10 million with quantitative confidence. The scaling race began immediately. So 2022, Hoffman at DeepMind publishes training compute optimal large language models. Yeah. So the paper its finding was that GPT-3 was suboptimal. It had too many parameters and too little training data for its compute budget. Again, I need to repeat this one. So it has so for example, they found out that GPT-3 has too many parameters and too little training data, yeah, for it is compute budget. So the ratio, the approximate 20 training tokens per parameter, like for example, 7 billion to 140 billion tokens, optimal for training compute. Your 70 billion module to 1.4 trillion tokens, optimal for training compute. Yeah, so DeepMind trained Chinchilla 70 billion parameters on 1.4 trillion tokens, and it outperformed GPT-3, which is 175 parameters with 300 billion tokens. Now, on nearly every benchmark, so a smaller, better trained model beat a larger, under-trained one. So the meta strategy insight, why overtraining is rational. After Chinchilla, Meta made a deliberate choice to train Lima 3 70 billion on a 15 trillion tokens. So over 200 tokens per parameter, far beyond the Chinchilla optimal. Now, why the Chinchilla ratio optimizes for training compute budget? It tells you how to maximize performance per training dollar, but it completely ignores inference cost, which is paid continuously for the model's entire operational lifetime across millions of users, billions of queries. Now, a model trained beyond the Chinchilla optimum on more data produces a smaller model with equivalent capability. Lima 3 70 billion trained on 15 trillion tokens matches or exceeds a 140 billion model trained on 7 trillion tokens at half the inference cost per query. Since inference is paid forever while training is paid once, the economics heavily favor overtraining. This insight is now standard practice across the industry. It is why you see 7 billion models being trained on a 10 million trillion tokens rather than a 100 billion that Chinchilla would suggest. Yeah. So the practical message for architects here is when evaluating modules, yeah, parameter count is less important than training token count and training data quality. So this is very important. Parameter count is less important, yeah, than training token count and training data quality. So these two are very important compared to the parameter count. So a 70 billion model on 15 trillion token of curated data will outperform, again, 70 billion to 175 billion model, which was trained on 300 billion tokens instead of trillion of noisy web data on almost every benchmark. Always ask both numbers. So when you look at the model, you need to look on both models. The training, the total training token, and the curated as well number. So this is a critical part. So with the scaling picture clear, let us look at what training actually costs in real dollar on real hardware with real models. Now, the cost of training. So we are going to try to have some understanding. It might take time to get hold of it, and it's not an easy topic, and most of it is like from estimates, and also because companies they don't disclose their cost, what it costs them, and what the breakdown of the money is. Of course, is but where people estimate them and they put them on papers, and so but it gives us like good understanding when you try to choose between the models on the market. So that's why I'm trying to to give you like as much information as possible. The information I got from these papers and not from the disclosure of the company, because as I said before, they don't disclose. You don't see if you search for the breakdown of the costs, you don't find them anywhere. So let us try to the estimation of the training cost. How much does it cost the training? So they come up with this formula of if you have the parameters times training tokens, yeah, times 6. Now, if you divide this one by like GPU throughput times GPU utilization, and then you multiply the whole lot by the GPU hour rate, it will give you roughly the training cost. Yeah. Now, the factor of 6 is the one we saw before. Remember when we're talking about the parameters which they change the parameters or the weight as well, and then they see the result, and then this is called the forward one, and then they compare it with the error, how much error is from the expected one. So, and then to minimize that error, they go back and change the parameter they used initially, and they keep continuing until the error is the smallest. And this is the gradient descent, they call it. So you have backward and forward. And in this here, the two operations for the two represent the two for the forward pass, and the 4 is for the backward pass. Yeah. So gradients are most expensive to compute. Yeah. That's why they are there, because to make it like the gradient, the loss we're talking about is it requires a lot of compute power. So that's why it's been multiplied by 6. Now, GPU utilization is the fraction of a theoretical peak flops actually achieved. Yeah. So typically 35 to 55% for large distributed training due to communication overhead. Now, and memory bandwidth limit and the checkpoint synchronization. So utilization is the primary practical variable. Now, if you see the real numbers now work it through, for GPT-3, for example, that was 2020, the parameters, if you see like 175 billion parameters, and then they train it on the 300 billion training tokens. Now, the estimated cost was 4.6 million. Yeah. Now, at the time, it was shocking because of lots of money. But today, it's considered inexpensive. The model was significantly under trained by Chinchilla standards, only 1.7 tokens per parameter. Yeah. So if you compare the parameter and the training tokens, yeah, it is 1 to 1.7 or 1.7 tokens per parameter. Now, Lima 2, which is 2023, with 70 billion parameters, and it used like 2 trillion tokens for its training. The estimate cost is 2.2 to 3 million. Note a similar parameter to GPT-3, but trained on 7 times more data per parameter. So training cost is scaled primarily with token processed. Yeah. So Lima 3, which is 2024, with again 70 parameter, but 15 trillion tokens. Yeah. The estimate cost is 15 to 20 million. Same architecture, but 7 times 5 more data than Lima 2, roughly 7 to 8 more higher cost. Yeah. Then the result is dramatically better model at identical inference costs. Yeah. So now GPT-4, which is 2023, the estimated one was 1.8 terabyte trillion, 1.8 trillion parameter, and 13 trillion tokens, and therefore the estimated cost was 100 to 200 million. So OpenAI has confirmed none of these figures, of course. So these estimates came from reverse engineering via published capabilities evaluation. So API pricing, which must cover training amortization. So and GPU allocation reports from cloud providers. So treat them as informed estimates, plus or minus 50%. Yeah. So Gemini Ultra in 2023 estimated 1.5 trillion parameters, which is and 15 trillion tokens. So the estimate cost here is like 150 to 250 million dollars. So Google has disclosed nothing about training details as well. Yeah. So Claudia 3 Opus, which is 2024, the estimated is 2 trillion parameters. Yeah. With 20 trillion tokens. And the estimate cost is $200, 200 to 300 million dollars. Yeah. So again, Anthropic has disclosed nothing as well. So now, the hidden cost multiplier, why headline numbers are misleading. So every cost figure above represents the single final training run. The actual total development cost is 3 to 10 times higher once you account for research and ablation studies, testing architecture, variant, hyperparameter search, data mixture experiment. For a frontier model, this typically involves 30 to 50 smaller runs at 1/10 of the final scale, costing tens of millions. So failed or unstable runs, loss spikes, and training instability are common. So a run that diverges after 60 days lost 6 days of compute cost. So most frontier training runs experience at least one significant instability event. So data pipeline, collecting, cleaning, deduplication, and quality filtering training data at, for example, at 15 trillion per token scale. This is months of work by a team of 20 to 50 engineers. So the engineering cost alone is the tens of millions. So human annotations, like you need tens of thousands of hours of human preference labeling, expert annotators for technical domains, law, medicine, code, cost 50 to 100 dollars per hour. A comprehensive human in the middle test dataset requires 50,000 to half a million labeled comparisons. So safety evaluation, a systemic red teaming and safety evaluation of a frontier model takes 6 to 12 months and involves dedicated teams of researchers. So total development cost for GPT-4 plausibly 1 to 3 billion once all of the above is included. Yeah. So it's not a million, it's 1 to 3 billion. So we include the above uh, uh, side of it. So only 5 organizations globally have the capital, talent, and infrastructure to operate at this level. Now let us look at the physical infrastructure that drives this cost. What does a training cluster actually look like? Now, the hardware reality, the GPU cluster, which is physical scale. Now, a training runs for a 70 billion model on a 15 trillion tokens use approximately 2048 NVIDIA H100 GPU. Yeah, each 2448 NVIDIA H100 GPU. So each H100 is 80 GB HBM3 memory, yeah, 3.35 petaflops of PF16 tensor core performance, which is it costs like 30,000 at list price. Yeah, so imagine these are 2048 NVIDIA H100 GPU, and each of them have 80 GB HBM3 memory, 335 petaflops of PF16 tensor core performance. Now, this is one. So actual market price have been higher due to sustained demand. So NVIDIA order backlog exceeds 12 months for most of 2023-24. Now, 2048 HA100 at 30,000 each. This is 61.4 million in hardware for this cluster alone. So again, the 2048 at 30,000 each, yeah. So this is just this one is like 61.4 million hardware for this cluster alone. So this hardware is typically shared across multiple training runs and multiple projects. So the per run hardware cost is amortized, but it illustrates the capital barrier to entry. So this GPU don't operate in isolation. With each 8 GPU server node, they are connected by an NVLink, NVIDIA's proprietary interconnect, at 900 GB per second. Total bandwidth between nodes, they use InfiniBand at up to 400 GB per second. So InfiniBand costs 5 to 10 times more than the standard Ethernet, but provides the near zero latency required for gradient synchronization across thousands of GPU, happening thousands of times per second. Now, this is one area. You can see the demand, the high demand. So you have two, we saw two things now, the GPU and how many memories it requires, and then the link as well, and it is the speed, yeah, and the costs associated with that one. So now this is another big problem. Yeah, the power, the physical limit is the power. So 2048 H100 at approximately 700 watts each. So which is 1.4 megawatts at GPU level. Imagine. So the power it requires 1.4 megabyte at GPU level. Add power, distribution infrastructure, cooling system, networking, and compute management. Approximately 10 to 15 megawatts total draw for the training cluster. So 15 megawatt for 90 days, which is 32,400 megawatt per hour. At UK commercial rate, for example, it is in UK you have 15 pound, 15 p, 15p per kilowatt hour. So we are talking now here 15 megawatt for 90 days is 32,400 megawatt per hour. So in the UK, this 32,400 megawatt per hour costs 4.8 million in electricity. And at US commercial rates, which is 8p per kilowatt per hour, it costs 2.6 million. So electricity is significant, but typically 15 to 25 of total compute cost. Yeah. So again, we are not considering the environment effect now. So how much energy we are spending on this side. So now let us see the other side, the GPU rental charge dominance. Yeah. Now fault tolerance. Now hardware failure is expected, not exceptional. In a cluster of 2048 GPU running 24/7 for 90 days, hardware failure are daily occurrence. GPU memory errors, PCI connectivity failure, power supply faults, overheating events, InfiniBand port failure. So each can hold a training run without proper handling. So modern training framework, which is the Megatron LM, deep speed, fair scale, checkpoints training, state every 10 to 30 minutes. When a failure occurs, the run restarts from the most recent checkpoints, losing at most 30 minutes of compute rather than the entire run. So a 9-day training run typically experiences dozens of interruptions. This operational complexity, managing a live 2048 GPU system for 3 months with no significant unplanned downtime, is why dedicated infrastructure team exists at AI labs. The skill set is closer to industrial plant operation than software engineering. Now, with the cost and hardware picture clear, let us step back and look at the complete training life cycle, the 5 phase that takes a model from raw data to deploy a product. The training life cycle here. Now, every production LLM has passed through 5 distinct phases. Each has different tooling, different teams, different cost profile, and different durations. Now, phase one is the data collection and tokenization phase. It will take weeks to months, and it costs like 1 to 5% of the total budget, maximum 5%. Now, this one is the data foundation. Here, quality is very important, and therefore, the common crawl provides raw web data. For example, you have web data, you send the crawl and it's just collecting those data. So what you need to do is like you need to do extensive filtering, deduplication, and quality scoring, which reduces to the mess of the web data into usable form. So the output would be a cleaned, tokenized, shuffled dataset of trillions of tokens ready for training. Now, this is phase two now, pre-training. This takes months, and this is like 60 to 75% of the total budget. Here, it is self-supervised next token prediction on the full training corpus at the maximum scale. So computationally, this is a dominant phase. At the end, the model has encoded language patterns and world knowledge, but cannot yet follow instruction or be helpful as an assistant. So this is the pre-trained one. And now phase 3 is the supervised fine-tuning. It takes days to weeks, and it costs like 5 to 10% of the budget. So instruction response pairs teach the model to follow the format of a helpful assistant. So you get instruction, you get a response. So this pairs, then teaches the model to follow the format of a helpful assistant. So the transition from I can complete the text to I can answer your question. So you move the token from the training from I can complete text to I can answer your question. Now phase 4, the alignment phase, which is the constitutional AI. So it takes weeks, 10 to 20% of budget. Human or AI generated feedback is used to align model behavior to human preferences. So helpful, honest, harmless. This is what transforms a raw language model into a product you would deploy. So it should be very helpful, honest, and harmless, of course. So this is the way the alignment is called. This is phase 4. Now, phase 5 is like evaluation and deployment. So ongoing, it is it continues. It's not like it doesn't have like a specific end date for it. The phase 5 is a continual process. So but it consumes 5 to 10% of your budget. This is the benchmarks, red teaming, safety evaluation, gradual rollouts, production monitoring. Now, the key strategic insight here is pre-training dominates cost at 60 to 75% of budget. Fine-tuning and alignments are cheap by comparison. This means the expensive capability foundation is built once at enormous cost by a handful of organizations, and the useful assistant behavior is built on top at a fraction of the cost. So fine-tuning and alignments are highly leveraged investment, like 5 to 20 million to shape the output of a 200 million foundation. Now, this is why organization can take Meta Lima 3, a free open weight foundation model, and fine-tune it for their specific domain at relatively modest cost rather than training from scratch. Now, let us go deeper into phase 1 and 2, data collection and pre-training, where the model's foundational capabilities are established. So data collection and the pre-training side as well. So what the data pipeline actually involves. So Common Crawl, the primary web crawl dataset, provides approximately 2 petabytes of raw HTML per month. Yeah, so it provides 2 petabytes of raw HTML per month. Sounds like unlimited high quality data. The reality is a raw command crawl extracts contains approximately 60 to 70% boilerplate, navigations menu, cookies notice, advertisement text, and so on. So significant duplicates and near duplicate content. So the same news article reprinted on 200 aggregators, low quality spam, CEO generated uh, gibberish, and personally identifiable information that must be removed. So quality filtering reduces raw web crawl by 60 to 80% before it is usable for training. The filtering criteria matters enormously for model quality and are actively researched. So the quality heuristic used by the different lab are among their most closely guarded competitive advantage. Now the training data mix, why IT determines competence now. The final dataset is a carefully curated blend for model like Lima 3, web text 45%, broad coverage, contemporary language pattern, diverse topics. Yeah, books are like 18%, long form, coherent, reasoning, narrative structure, formal register, code, like it is 15%, programming languages, documentation, structured problem solving, academic papers 10%, technical depth, scientific reasoning, citation, awareness, Wikipedia, and curated knowledge is 7%. Reliable factual content, encyclopedic structure, other multilingual, legal, specialized is 5%. So the mix determines competency profile. A model trained on 15% code is dramatically better at programming than one trained on 2% code. This is directly actionable. When evaluating models for code generation, ask about the code percentage in training data. So when evaluating multilingual capability, ask about the target language representation. So pre-training is what the loop looks like. So the mechanism is simple. Show the model a chunk of text. Ask if it predicts each token from its left context. Compute cross entropy loss between prediction and true tokens. Backpropagate gradients. Update parameters by a tiny amount. Repeat for 15 trillion tokens. So on 2048 GPU for 90 days. So that's what you need to do. So What is not simple here is maintaining numerical stability over month-long training, preventing loss spikes that corrupt the model state, ensuring gradient communication across 2048 GPU does not become a bottleneck, managing the checkpoint infrastructure and monitoring hundreds of training metrics to catch instability early. So self-supervised learning, the elegant property, the training requires zero human labels. The correct answer for every training step is what is the next token is already in the data. So the model can train on the entire internet text without any human annotation. This is what enables training on trillion tokens corpora at all. So human labeling at that scale would be impossible. Now, after pre-training, the model has language knowledge, but cannot follow instructions. So fine-tuning bridges the gap. Now, the fine-tuning is very interesting one, and the problem fine-tuning trying to solve is a base pre-trained model is remarkable. It has encoded world knowledge and language pattern, but it also slightly problematic. Ask it, what is the capital of France? And a row-based model might respond, what is the capital of Belgium? What is the capital of Germany? Because it has seen questions listed in its training data and is predicting what typically follows a geographical question, not answering it. So supervised fine-tuning creates instruction response pairs, input as an instruction, summarize this article in 3 bullet points, and then response is the desired output. So after a while, on the thousands to millions of such pairs, the model learns the instruction following format. So full fine-tuning, costly but complete. Full fine-tuning updates all parameters for a 70 billion model. This requires nearly as much compute as the original training hardware, equivalent to 40 to 80 A100 GPU. Estimate cost for full fine-tuning of GPT-3, 175 billion. So approximately 2 million. This is prohibitive for most organizations. So LoRa, the efficiency revolution. So LoRa, low rank adoption is 2021, is one of the most practically impactful papers in recent AI research. It is insight instead of updating all weight metrics, which is weight metrics, add two small trainable metrics, which is A D times R and B R times K alongside each weight, where R stands for rank is much smaller than D or K. The effective weight updates is B times A because R is small, typically A times 64. The number of trainable parameters is tiny. So for 70 billion model with LoRa at rank 16, trainable parameters 70 million versus 70 billion for full fine tuning. So this is 0.1% of the original parameter count, memory reduction by 10 to 100 times, GPU requirement 1 to 2 A100 versus 40 to 80 for full training. Estimated cost 10,000 to 50,000 versus 2 million for full fine tuning. So the quality on most downstream tasks is competitive with full fine tuning. So Microsoft original LoRa paper demonstrates near identical performance to full fine tuning on multiple GPT benchmarks. So the open source community has since validated this across dozens of model families and hundreds of tasks. So when to fine tune versus other approaches. So decision trees for architect, problem solvable with prompt engineering alone, use prompts, cost near zero, consistent output format or style needed at scale. Few short prompts or but with LoRa cost low. So domain knowledge not in the base model. SFT plus RAG cost moderate, specific model behavior, counterproductive for your use case. Now, when not to fine tune, if you need the model to know about recent documents, fine tuning will produce mixed results. The model may memorize surface patterns from documents it was fine tuned on, but will hallucinate related facts it didn't memorize. For factual grounding, RAG is for far more reliable than fine tuning. Now, fine tuning gives task capability, alignment gives safety and helpfulness. These are fundamentally different engineering problems. The alignment problem, yeah. After SFT, the model can follow instructions, but it may still produce harmful output, be dishonest or be uh, not agreeable. So the challenge here is how do you specify helpful, honest, and harmless as a mathematical loss function? You cannot, helpful is, you cannot, of course, yeah, but helpful is contextual. Honesty conflicts kindness in some situation. Harmlessness involves prediction of downstream consequences that require world knowledge. So no closed form loss function captures human values. Additionally, naive optimization produces failures. A model optimized purely to maximize human approval ratings learns to tell users what they want to hear, regardless of accuracy. So a model optimized to minimize refusal agrees to generate harmful content. These are not hypothetical. They have been observed in production systems. Now, the human factor here. So we need to do humans to help us in this situation. So step number one is a preference data collection. So generate multiple responses to the same prompt. So human raters rank them A greater than C greater than B. Thousands to millions of such comparison pairs are collected across diverse prompt types. So the challenge here is raters quality varies significantly. So a rater evaluating a Python code snippet may not be a programmer. A rater evaluating a medical summary may not be a doctor. So rater inconsistency introduces noise. The quality of the preference data is the primary bottleneck. So example comparison. Explain quantum entanglement simply. And the response is a quantum entanglement is when two particles become linked such that measuring one instantly determines the state of the other regardless of distance. So, and the response number B could be it is a complicated quantum physics stuff. Basically, the practice are connected. So human ratings here is a clearly preferred. The reward model learns this signal. So step number two is reward model training. A separate neural network learns to predict a human preference ranking. Given n response, it outputs a scalar score. This model approximates human judgment at scale, allowing evaluation of millions of responses without human raters for everyone. So the reward model errors propagate into the final model. This is why reward hacking occurs. The RL optimizer finds response that score highly on the reward model, but that humans would actually rate poorly if they saw them. So Step number 3 is the RL optimization. The LLM generates response. The reward model scores them. PPO updates the LLM parameter to increase expected reward. So a KL divergence penalty prevents the model from diverging too far from SFT baseline. So without this penalty, RL produces degenerate high reward output that are unlike any plausible human text. So the alternative is the direct preference optimization, which had been introduced in 2023. So direct preference optimization is eliminated the separate reward model, uh, directly optimizes the base model on preference pairs by reframing the human side objective as classification problem, computationally cheaper, often comparable quality, widely adopted by open source community. So constitutional AI, Anthropic, the model critic and uh, and revises its own output guided by a set of principles, the Constitution. So reduces reliance on human preference labels and enables more consistent safety behavior across diverse prompt types. Now, the RL for AI feedback uses a strong AI model as the preference labeler instead of or in addition to humans. So it scales preference collection by orders of magnitude. Quality depends entirely on the labeling model's alignment. So what is the problem here is an active failure mode. So the human raters tend to produce uh, psychophonic models that agree with the user's state position regardless of accuracy, because human raters tend to rate agreeable responses more highly than accurate but disagreeable ones. This is an active research problem. All major labs are working on the solution. Now, with this foundation in the training process, let us look at the current model landscape. So we have introduced how these parameters and the trainings and the cycles of training and the complexity of the LLM, how it works. We have seen that bit. Now let us return back to what is all about, why we were just talking about all the stuff there. You can search the information which I'm providing it there. You might have more intuitive or more information, especially from university side. There's a lot of papers, researches, which you can read and also summarize, understand as well. So, but our the aim is for AI solution architecture here. So, how do you choose one model from the other? So this was like a feedback what you need to look before you choose a model. So that is the one. So we are going to look now. We are going to choose like 10 most popular LLMs, and we are going to compare them. Yeah. So the fundamental framing here is there is no universal best model. That's the key part here. No. So there is nothing called this is the best model in the world. Yeah. So it is a comparison, so you can look the parameters they have used, how many tokens they have trained, the cost, and also the energy which it consumes, and so on. I mean, you could have different kind of need when you compare those LLMs. So let us look. The most common mistake in model selection is treating it as a single answer question. So there is no universal best LLM. This is a very important one. Different model makes different trade-offs. Yeah. So the correct question is always, given our specific use case, the latency requirement, data privacy constraints, budget, and quality threshold, which model is optimal. So that's what we need to see. Yeah. So that our says the use case, yeah, specific use case, how many latency we are what is the latency requirements, the data privacy constraint, budget, and quality threshold. So GPT-4 Turbo, for example, OpenAI, the general benchmark, estimated, for example, it has 1.8 trillion parameters in a mixture of expertise architecture, excellent across reasoning, coding, instruction following, and multimodal task. The model other vendors compete against is like, yeah. So all the other models we saw, they compete against GPT in terms of it is cross reasoning, coding, instruction following, and multimodal task. This is one. Its weakness is $10 input and $30 output per million tokens makes it expensive for high volume application. So it's key here is like for input you pay £10, $10 for output you pay 30, and this is per million tokens. Yeah. So that's so if you have a very big number, we saw it before. If you have, for example, a document which have 10,000 words, and then if you want to process 100,000 of the same document, then it costs you a fortune. Now, the second one is Claude 3 Opus, which is Anthropic, yeah? Known for non-instruction following, reduced the syncophancy compared to GPT-4, and the largest context window among the proprietary models at 200K tokens, enabling full book analysis in a single core. So Anthropic's constitutional AI training produces notably consistent safety behavior. Its weaknesses is slowest inference and highest price in this table. Yeah. Gemini Ultra, which is Google, the multimodal specialist, natively trained on audio and image, video, and text simultaneously, not separated models stitched together. So 1 million tokens context window. Knowledge cutoff is November 2024, the most current in this table. So weaknesses is API availability has been more restricted than competitors. Yeah. So Llama 3, which is 450 billion, which is the meta, we call it the best open weights model as of early 2025. It has 405 billion parameters, 128K contexts, competitive with GPT-4 Turbo on many benchmarks, freely downloadable for self-hosting. This is a key part. And then the foundation of the open source LLM ecosystem. Weakness requires 8 plus H100 GPU for inference, not accessible without significant GPU infrastructure. That's a problem. So DeepSeek, which is version 6, DeepSeek AI, the cost efficiency story of 2024 to 2025, 671 billion total parameters, 37 billion active per token, 14p input, 28p output. It is 107 much cheaper than the output than GPT Turbo. So performance competitor on coding and reasoning. Note Chinese company, data sovereignty consideration for some organizations. So Mistral Large 2, Mistral AI, efficient 123 billion dense model, strong performance above its parameters class. 2 to 6 input $2, output $6 per million tokens. A strong cost quality ratio for European deployment, French company with EU data residence options. Now, Queen is 2.5, 72 billion. Alibaba leads Chinese English multilingual benchmark trained on 18 trillion tokens, highest training data volume in this table, self-hostable on a 4 to 800 GPU, strong mathematical reasoning. Now, Command R is coherent, is purpose-built for enterprise RAG, grounding and citation built into the model design. You need like $3 for input, $15 for output per million tokens. So optimized for retrieval, augmented generation pattern when you need the model to explicitly cite sources from provided documents. So Grok 2 real-time data access via X data pipeline included with X premium subscription, strong conversational capability. So Neomotron 4 and NVIDIA optimized for synthetic data generation, creating training data for other models, open weight, 340 billion parameters. So the selection framework is cost-constrained high volume, which is DeepSeek V3 or Mistral Large 2. Privacy critical, healthcare, legal, finance, Lima 3, 4 or 5 billion, or Queen 2.5, self-hosted long document analysis, Claude 3, Opus multimodal, video, audio, images, Gemini Ultra. Multimodal is the Gemini Ultra. Chinese English multilingual is Queen 2.5. Enterprise RAG with citation is Command R+, and the general purpose best quality data not sensitive GPT-4, Turbo, or Cloud 3 Opus. Now, beyond parameters, let us look at the metrics that actually drive day-to-day architectural decision. Now, cost, speed, knowledge metrics. So the cost disparity, the number that matters most. So GPT-4 Turbo output for the output, it costs you $30 per million tokens, while DeepSeek V3 for the output, they charge you like 28 cent per million tokens. Now, if you see these two, what you see is like that is 107 times difference in output costs. So at what volume that this became financially material, if you ask? So say, for example, an enterprise chatbot processing 10 million output token per day. So GPT-2 Turbo will cost you $300 per day, which is going to be 109,500 per year, while DeepSeek V2 will cost you is cost $2 ATP, 8 cents per day, which is in the whole year it costs you 1,022. Now the annual difference is staggering. So this one just for the enterprise chatbot, if you go to GPT-4 Turbo, it will cost you more by 108,478. So for a use case where DeepSeek performs comparably to GPT-4, which is, for example, for classification, extraction, and standard question answer, it typically does. This is a straightforward decision. The quality gap between frontier and second-tier models only becomes apparent on the most demanding tasks, complex multi-step reasoning, subtle instruction following, or creative writing. Now, never assume you need the most expensive model. Always benchmark your specific task before committing. Yeah. So a 10 prompt test across candidate models for your actual use case is worth doing before signing a commercial contract. Now, knowledge cutoff, which is the invisible constraint as well. So every model has a cutoff date after which its training data was not collected. Events, laws, research, products, and people that emerged after this date are invisible to the model. So more precisely, the model has no statistical knowledge about them. So meaning it will either refuse if it is well calibrated or confidently hallucinate if not. So Gemini Ultra November 2024 cutoff is the most current in this table. Even that it is months behind today. For any application involving current events, recent regulation, or updated product information, you need either RAG, which is to retrieve current documents and include them in context, or a model with real-time search capability, like Grok 2, for example. Now, the other one is speed. The user interface variable time to different token matters in interactive application. So if it is an interactive application, the response, the time is very critical. So Cloud Opus is like 5 to 8 seconds to start responding. Well, is acceptable for a document analysis, but frustrating for live chat. DeepSeek v3 is under 1 second, provides a substantially better interactive experience. So the speed difference is architectural. Dense models activate all parameters per token, more competition, higher quality ceiling, slower throughput, and it can activate 5 to 6% of the parameters per token. So far lower competition, far fast throughput, and quality competitive on most tasks. Now, the practical architectural recommendation would be you need to separate analytical and interactive workloads. So use a high quality, slower model for batch processing, complex reasoning, and high stake decisions. Now, on the other hand, use a fast, cost-efficient model for real-time interaction, autocomplete, and classification. So the same model for both workloads is rarely optimal for either. So one of the most consequential strategic decision when you deploy LLM is open weight versus proprietary API. So let us work through it with the real numbers. So the open weights versus proprietary. So this is a strategic decision with technical, financial, legal, and operational dimension. It is not primarily a technical question. The correct answer depends on your organization's specific constraint. And for most mature organizations, the answer is both in different contexts. Now, the privacy argument, often legally determinative, when patient data, financial records, or attorney-client communications, or other regulated data is involved, the question of data sovereignty is often legally resolved before any technical evaluation begins. So using a proprietary API, GPT-4, Claudia, Gemini, means sending data to a third-party server, even transiently. In the UK, the GDPR Article 46 requires adequate safeguards for third country data transfers. In healthcare, HIPAA requires business associate agreements. EU AI Act in force 2024 adds additional obligations for high-risk AI applications. Say, legal teams at regulated organizations routinely conclude that proprietary API cannot be used for regulated data categories without a specific contractual protection that are not universally available. Now, open-weight model is self-hosted on-premise or private cloud infrastructure solve this cleanly. The data never leaves your control. Llama 370B processing medical records on your own hardware had the same compliance posture as your existing internal systems. So the capability argument, the gap is closing. In 2022, the gap between proprietary frontier models and best open weights models was large. GPT 3.5 dramatically outperformed anything freely available. By 2024-25, the gap has now significantly. Llama 405B competes with GPT-4 Turbo on many benchmarks. DeepSeek V3 rivals GPT on coding tasks. Queen 2.572 billion outperforms GPT-4 on Chinese language tasks. So the trend, open weights models typically lag proprietary frontier models by 6 to 12 months. So for most enterprise use cases which do not require absolute frontier capability, open weights is increasingly viable from a quality standpoint. Now, the break-even economics at low volume, less than 100 tokens per month, proprietary API wins on total cost. So this is again very important. At low volume, which is less than 100 million tokens per month, proprietary API wins on total cost. You avoid GPU capital expenditure, engineering time for infrastructure management, and operational overhead. The API cost at this volume is modest. So at a medium, from 100 million to 1 billion token per month, model and use case depends, runs the number for your specific situation. At high volume, though, which is greater than 1 billion token per month, open weights typically win. A single A100 GPU running Llama 370B into 4 process approximately 5 to 10 million tokens per day. So amortized hardware plus electricity roughly $1 per day. IGBT output price in 30. Equivalent volume would cost 150 to 300 per day. Break even is approximately 500 million per billion output token per month. So the hybrid architecture recommended for most organizations is most mature LLM deployment use a hybrid strategy. Proprietary frontier models for high-stake, low-volume, complex tasks, like, for example, contract analysis, complex code generation, non-escalated support, interactions, open weights for high volume, cost-sensitive, medium complexity tasks, classification, extraction, structured summarization at scale. So this architecture optimizes quality where it matters and cost where volume is high. Now, we have mentioned a mixture of expertise several times. It deserves a dedicated deep dive. It is reshaping the efficiency landscape. So, mixture of expertise, MoE. The core insight here is the specialist efficiency. A hospital with a separate specialist department, cardiology, neurology, oncology, provides better care per doctor hour than a hospital where Every doctor must be competent at everything. For anything patient presentation, only the relevant specialty is activated. The others are not wasted. So they are available but not consuming resources for these patients. So apply to neural network. Instead of one dense feed-forward network that processes all input patterns using all parameters, use many specialized expert networks. A lightweight router network decides which experts are most relevant for each token and activates only those, so the others remain dormant. So the mechanics in details in a standard transformer, the feed-forward network, accounts for approximately two-thirds of total parameters count. In mixed transformer, mixed of experts transformer, the FFN, which is the feed-forward network, is replaced by N experts, FFN plus a gate network. For each token, the gating network output of a probability distribution over experts and selects the top K. Typically, K is 2. So DeepSeek V3 specific total parameters is 671 billion across 256 experts. Now, active parameters per token is 37, gating network plus attention plus 2 selected experts. Fraction activated per token, inference compute cost equivalent to 37 billion dense model. So knowledge capacity is equivalent to 671 billion dense model. So the router learns to specialize during training. Research on trained models shows that different experts cluster around different content types. So some specialize in code pattern, others in factual records, others in reasoning chains. So this specialization is learned from data, not programming. So load balancing, the critical engineering challenge. So mixed of expertise, primary failure mode. If the router learns to always send all tokens to the same 2 to 3 experts, those experts receive all the gradient updates and improve while others are wasted. So the model effectively become a small dense model with useless capacity. So modern mixed of expertise implementation use auxiliary load balancing losses, additional training objectives, terms that penalize uneven expert utilization. So DeepSeek V3 uses sequence level load balancing that ensures each expert receives roughly equal total token volume across training batches without constraining individual token routing decision. Getting this balance right is one of the key engineering achievements. So why multiple of expert explains uh, DeepSeek's pricing? Inference cost scales with active parameters, not total parameters. So DeepSeek V3 has 374 billion active parameters, cost approximately the same to run as 37 billion dense model, while having 671 billion parameters worth of capacity available for training. This is why DeepSeek can price at 28 cent per million output token while achieving quality competitive with models that cost $30 per million. The economics fundamentally shift with multiple of expertise. So for architecture, multiple of expertise models are ideal for high quality, high volume applications. They are less ideal for ultra low latency requirements. Router decision adds overhead, and expert selection introduces non-deterministics that can complicate debugging. So let us close with 6 trends that will define the next 24 months of this landscape. Now, the feature 6 trends. Trend number 1, context window. So 1 million context to 10 million plus tokens. Now, context window grew from 2,048 tokens in 2020 to 1 million tokens in 2024, which is a 500 times increase in 4 years. The limiting factor is quadratic attention complexity, HBM memory, KV cache size, so are actively being addressed through sparse attention and linear attention variation. So the 10 million plus token context window are technically plausible within 12 to 24 months. At that scale, the use cases are qualitatively different. An entire company's email archive for a year, a complete software code base for a security audit, a comprehensive medical record for birth to present. So this is the one which we are expecting in this year or 2 years. So now the medical records is very interesting. A comprehensive medical records for from birth to present. So the application shift from document level to organizational level analysis. Now, trend number 2 is native multimodality. Current multimodal models encode images as visual tokens appended to the text sequence. Effective but architecturally awkward. So the emerging approach is train from scratch with interleaved text, image, audio, and video data. So all modalities share a unified representation space. So Gemini was built this way. The practical difference is native multimodal models perform spatial reasoning about images and temporal reasoning about video and cross-modal analogical reasoning that stitches across architects struggle with. Yeah, so the trend number 3 is the smaller but smarter distillation and synthetic data. So a 7 billion model in 2025 perform tasks that require a 7 billion model in 2023. So the mechanism is better training data, specifically synthetic data generated by frontier models. To train a small student model to initiate a large teacher model reasoning. So not just predict the training corpus, but replicate how very capable model approaches problems. So Microsoft Phi series and Alibaba's Queen series have demonstrated that 3 to 7 billion parameter models can match much larger models on targeted tasks through careful distillation. So trend number 4 is test time compute scaling. So OpenAI series introduced a new scaling access. Instead of scaling training compute to build a larger base model, scale inference compute by giving the model time to think before answering. Train with reinforcement learning on a process reward model that rewards correct reasoning steps, not just a correct final answer. At inference, the model generates extended internal reasoning trace before responding. So more compute at inference is equal more answers on complex problems. So this is a significant shift, capability improvement delivered at inference time rather than training time. So train number 5 is agentic capabilities, transition from LLMs as reactive question and answer systems to autonomous agent is underway. An agent calls external tools, web search, code execution, database queries, API calls, maintains state across multiple step tasks, plans sequence of actions, and verifies its own output. Near-term practical applications, so software development agents one writes code, run, test, debug iterative without human involvement at each step. So data analysis agent, query, visualize, narrate, research agent, which is you can research, read, synthesize. The engineering challenge, though, is reliability, safety, and evaluation are significant but traceable. So trend number 6 is cost reduction. So the 428 trajectory, GPT inference cost was $60 per million tokens in 2020. Turbo GPT-4 Turbo $10, DeepSeek 14 cents. The cost per million tokens has dropped 428 times in 5 years. If this trajectory continues at even half its historical rate, frontier quality inferences cost under 10p per million tokens within 2 to 3 years. That unlocks applications that are economically impossible today. Real-time LLM assistant embedded in every software interface, continuous background analysis of every document in an organization knowledge base. So cost reduction is not just a pricing benefit, it expands the addressable application space by orders of magnitude. Now, the 5 final takeaways for solution architecture. Scale is staggering, but democratizing simultaneously. So frontier training costs billions, 7 billion models run on laptops. Both are true today. So scale is staggering, but democratizing is also simultaneously increasing with that one. So frontier training costs billions. That's we know that. So, but the 7 billion models run on laptop. Both are truly today. So this is number 2 is like the training pipeline determines the model's capability and failure modes. So pre-training data shapes knowledge. So fine-tuning shapes behavior and alignment shapes value. So understand the pipeline, understand the model. So this is again a critical bit. So pre-training data, the pre-training data as we saw it before, it shapes the knowledge as we know, yeah? Now, if you start fine-tuning, and now it shapes the behavior. Now, if you add the alignment, it shapes the value. So understanding the pipeline is also understand the model. So there is no universal best model optimized for your specific constraint. If you cost, quality, latency, privacy, language, and modality. This is the driving force for you so as a solution architect, AI solution architecture. So how much it costs, what is the quality you expect from them, the latency, the privacy, the language, or the modality. So multiple of expertise is rewriting the cost curve. So 671 billion total parameters at 32 billion active per token is the current efficiency frontier. This changes what is possible at what price. Now, the architecture for the cost trajectory, not today's price. Applications uneconomical at $10 per million tokens will be economical at 10 cent per million tokens within 2 to 3 years. Build for that future. So thank you. I'm happy to take questions. The question I find most productive. So given what we covered today and what would you do differently in the project you are currently working on. So thank you again for listening. It was a little bit involving topic. I hope it lights some shade on certain areas and clarify certain areas as well. I'm sure some of them might not be clear now, but as you delve and search more, it will be much clearer. So see you next. We'll do the next part is going to be more on the practical side of LLM. So we are going to see the one we just discussed, the free one and the paid one as well. So we are going to test them using different scenarios. See you next.